The carbonyl carbon in monosaccharides can be easily oxidized, for example, by copper plus 2 ions. If you would add glucose solution to bright blue and transparent a solution of copper salts, it will immediately turn into turbid rusty red, because the aldehyde group of glucose, which reversibly condenses and decondenses between circular and linear form, will be able to efficiently reduce copper 2 ions to copper plus 1 state, forming copper oxide, which falls out in the pellet as this rusty red uh, the rusty red turbid substance. This is actually known as Vechlin test and used as a test for reducing sugars. Nevertheless, not although all monosaccharides are reducing, not all the sugars are reducing. For example, monosaccharides locked in hemiacetal or hemiketal state can use anomeric carbon to form a bond with a carboxy group of another monosaccharide residue, forming so-called glycosidic bond. Formation of this bond turns the liable hemiacetal state of anomeric carbon to stable acetal state. These condensation reactions have very high activation energy and catalyzed by specific enzymes. By being locked in hemiacetal or hemiketal state, the residue with this anomeric carbon engaged in glycosidic bond cannot easily linearize, exposing its aldehyde or keto group, and this way cannot be oxidized. The reducing ability is used in a naming convention to define the condensates between monosaccharides. The reducing end, non-reducing end, sorry, is shown by convention on the left, and the reducing end on the right. For example, if you take disaccharide maltose, which is a condensate between diglucopyranose units, the left residue is locked in a full acetal state, forming glycosidic bond with the fourth carbon of the next residue. Because the non-reducing end is locked in full acetal state, the anomeric form has to be specified because it cannot reversibly exchange between two anomeric forms. In this case, it is alpha anomeric form. The reducing end residue is shown, and in naming convention is shown on the right, and in this case the anomeric form doesn't have to be specified because it can reversibly decondense and exchange between two anomeric forms. In the middle, in brackets, there is specification of the direction of glycosidic bond from which atom, carbon atom, in the non-reducing end to which carbon atom in the reducing end the glycosidic bond stretches. And to underscore the direction of glycosidic bond, the arrow, it is indicated by arrow, indicating that the direction of bond is from non-reducing to reducing end. Maltose, as such, is still a reducing sugar because one of the ends is reducing, and it will be positive in Vechlin test. However, not all the sugars, or to be specific, not all the disaccharides are reducing. Let's look at some examples. Let's take lactose. Lactose is a condensate between two residues, one galactose residue and one diglucose residue. The galactose residue is locked, is in this case in beta anomeric form, and is locked to fourth residue of glucose by the glycosidic bond. So the galactose residue um, is non-reducing end and is not well, it's not reducing. However, the the glucopyranose residue still have anomeric carbon free, so it could be oxidized, so it forms reducing end, and this will be altogether reducing sugars. Of note, the long naming of monosaccharide condensate sometimes shortened by conventional naming of common forms of sugars with three-letter abbreviation. For example, the glucopyranose is abbreviated as GAL, and the galactopyranose is abbreviated as GAL, and D-glucopyranose abbreviated with GLC. This way, the long names could be significantly shortened. Another example is sucrose. Sucrose is a condensate between D-glucopyranose and D-fructofuranose. In this case, the glycosidic bond stretches from one anomeric carbon to another anomeric carbon. In this case, both residues are non-reducing, and consequently this sugar will be a non-reducing sugar. And in this case, in the naming convention, the anomeric form of both residues have to be specified, and in case of saccharose, it is alpha anomeric form and beta anomeric form respectively. And the direction of glycosidic bond in this case is not defined because there is no reducing and non-reducing end. In this case, the direction of glycosidic bond is shown with double head arrow. Trecalose is also non-reducing sugar consisting of two the glucose residues which are locked with one another in alpha anomeric state, engaging both anomeric carbons. So it is also a non-reducing sugar. To sum up, the monosaccharides which could be present in solution as reversible circular condensates in hemiacetal or hemiketal form can, with the help of enzymes in biological systems, condense to one another via the anomeric carbon, converting the monosaccharide residues into full acetals or full ketals, linked to another monosaccharide residue with a stable glycosidic bond. Because of that, some of the residues in this condensate would have reducing property, and some of them won't have reducing property, and this used to name the monosaccharide condensate starting from reducing to non-reducing end.